All right, we're going to look at some notation here that's going to help us evaluate these sums that help us find area by compacting the sum into some smaller symbols. The sum that's used is this Greek letter sigma, which is the Greek letter S, which makes sense that we use the letter sigma to stand for sum. And so what we need to do is decipher what all this means. So if I have a sigma symbol, it's telling me to add up or to sum up what's inside. Now, what's inside is going to be an expression that's going to contain not a variable, but a parameter. And the parameter is going to be labeled on the bottom of the sigma. And what happens is the bottom of the sigma tells you where does that parameter start its value. And then at the top of the sigma, you are told where the parameter finishes. So what do you add up? You add the object at the value of the parameter where we start, and then we add the next value of the parameter. Okay, because the values of the parameter are going to go up by integer values. And then we continue adding until we get to the value of the parameter that's at the top of the sigma. So let's do some examples. Okay, here's an example with k over k plus 1 is my object that contains the parameter k. And the parameter doesn't have to be k, it can be any letter. So this says start your parameter at 3. So the first time around, this expression is going to have a value of 3 over 3 plus 1. Then we say add, and then the parameter value will increase by 1 each time. So the second time around, the value of the parameter is 4, so we'll have 4 over 4 plus 1. Next time around, we add 1 to the parameter value, and we're at 5 over 5 plus 1. And then the last object that gets added is 6 over 6 plus 1. So this symbol over here is a shorthand way of writing this object, or that sum here. Second example, this tells me the parameter value is k, but there is no expression that has k in it. There's just a number 2. So what does this mean to do? Well, let's pretend there was a k and we were keeping score. Okay, up here, when k is 1, what's the value of the expression? 2. So we're going to add, and then we're going to go up to the next level. When k is 2, what's the value of the expression? 2. When k is 3, what's the value of the expression? Still 2. And finally, when we get to k is 4, what's the value of the expression? Still 2. So that's not a very exciting example, but it's a possibility that we'll run into from time to time. And then the last example has not only the parameter k involved, but also a variable x. Important thing to note here is that the x is not affected by what's on the sigma symbol. This only affects the parameter k and increases the parameter by 1 each time. So when k is 1, we will get 2 minus 1 times x. We add, and we go to the next level. 2 times 2 is 4, so we'll have 4 minus 1 times x. Now k is 3, so now we'll have 6 minus 1 times x. And finally, when k is 4, we'll have 8 minus 1 times x. Now, let's take this and work it the other way, where we have a sum that we may not want to rewrite many times, or it's too long to write and we want to have a symbol for it so our calculator can evaluate it for me. First one's very easy. In all these examples, we want to look for things that increase by 1 each time. And if I can do that, then that's what my parameter k is going to stand for. So the first example is very easy. The numbers all increase by 1 each time. So this is going to be a simple case of saying, let's sum up objects that look like k, where k begins at 1 and ends at 10. Second example. Not quite as easy because I don't see the number 1, I don't see the number 3, and I don't see the number 5. I don't see any of the odds. So if I can rewrite this, then I can change the sum into a sigma condensed version of the same sum. So there's a couple ways you could do this. One way is to factor out a 2 from all these terms. And notice that now I have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. And since I now see the occurrences of numbers that increase by 1 each time, I'm in the position to use a sigma. And so you could do it like this, sigma 2 times k, where k begins at 1 and ends at 7. This third example has just the odd numbers. So now this one's a little bit different than this one, but it's connected. If the even numbers are represented by 2 times k, then an odd number is either going to be 2k plus 1 or 2k minus 1. So we could write it a couple ways, and that's the beautiful thing about sigmas, is sometimes there's multiple ways to write them. If we say 2k minus 1 is how you obtain odd numbers, then we would start when k is 1 to obtain 1 is my first thing to be added, and then we'll end when k is 10. 2 times 10 minus 1 would give us 19. Okay, an alternative way to write this would be to say sigma 2k plus 1. Now we'll have k start at 0, and we'll have k end at 9. And finally, let's do an example that has more than just these symbols in there. This one should have an f also, now that I look at it. Okay, what's increasing by 1 each time? That's the key to using the sigma. You need to find that quantity that increases by 1. So f is common to all terms. The first 1 in the parenthesis, or in the argument of f, is common to all terms. So those things are going to stay the same. And then I can see that if I look at it a little bit differently, this is 1 over 2, this is 2 over 2, this is 3 over 2, this is 4 over 2, 5 over 2, 6 over 2. So I have k over 2. The numerator of that fraction is the quantity that's increasing by 1 each time. And k will start at 1 and end at 6. Now, the point of all this is to be able to write a sigma that will represent the area of a region with a lot of rectangles instead of having to write it out by hand or use Microsoft Excel. Be able to get answers even faster. So we did this exact problem in class using Excel last time, and we'll compare our answers to make sure we're correct. So we have the function 1 over x between x equals 1 and x equals 2. This is the x-axis. And we want to approximate this area using a right Riemann sum and 1,000 rectangles. So remember, the first thing is to subdivide your interval into pieces. And I'm going to create a symbol here that we're going to use throughout this calculation. So how wide is each subinterval? Let's call that width delta x, like change in x. And the way in general that this is calculated is by taking your right endpoint, subtracting your left endpoint, and dividing by the number of rectangles. So in our case, delta x is going to be 2 minus 1 divided by 1,000. And we did this last class, so we know it's 1 over 1,000. But if the numbers were uglier, this is how you would calculate your delta x. Now, I'm going to just draw kind of a symbolic subdivision here because I can't draw 1,000 tick marks in here to separate this, but you'll see the pattern as we go. All right, we know that the first x value here is a 1. Now, I know that the next one, and you know the next one, is 1.001, 1 plus 1,000th. And we could write it like that. But instead, I'm going to write that as 1 plus a delta x. Because that's how far I've moved to the right from 1. I've moved delta x units. So that's the first tick mark to the right of 1. What's the next one to the right of 1? Well, one way to say it is 1.002. But another way to say it is 1 plus 2 delta x's. Okay, because what am I doing? Each time I'm going to move a delta x to the right from where I was before. And so each time I write a new x value, I can do it with a delta x that increases by 1 each time, and that allows me to use a sigma. And we would continue this until we got to the very end, which would be, in this case, 1,000 delta x's. Because I started at 1, and since I'm using 1,000 rectangles, I'll end up with 1,000. So let's write out the first few areas, and then we'll see the pattern develop, and then we can use the sigma notation. So the area approximation is approximately, okay, how wide is each rectangle? Well, we're using the symbol delta x. So the first height is going to be f of 1 plus delta x. The y value with the x value 1 plus delta x, which we could calculate because we know what the function is, but let's just leave it symbolic. Okay, the next rectangle will have an area of delta x times f of 1 plus 2 delta x. The next one will have an area of delta x times f of 1 plus 3 delta x. And then I'm going to put a plus sign and then 3 dots, which is an ellipsis, which says that this pattern continues. And then we'll say where it ends, okay? It ends at delta x times f of 1 plus, where do we end? 1,000, because I started at 1, and I need to have 1,000 rectangles, so the last one's going to be at 1 plus 1,000 delta x, which would get me to f of 2. Okay, so now sigma can write this sum condensed for me in a form that I can enter into a calculator. So what does the sigma look like? The delta x is common to all those terms. The f is common to all those terms. The 1 is common to all those terms. The delta x is common to all those terms. And the thing that changes, and it changes the correct way by 1 unit each time, is the number in front of the delta x. And so that's where our parameter k goes. K starts at 1 and ends at 1,000. Now let's jump to the TI Nspire, and we'll enter all this information in and see what kind of an answer we get. And then we'll compare it with the Excel spreadsheet that we saw last class. Okay, we're in the TI Nspire, so we want to do a couple things before we do the calculation. Number one, I want to store 1 over x as f, so the calculator knows who f of x is. I also want to store 1 over 1,000 as delta x, and in the calculator, let's just call that dx. And now we need to define where sigma is. Okay, in the menu, under calculus, you'll find sum, and up pops the Greek letter sigma. We have to tell the calculator who the parameter is, and k is the parameter that starts at 1, ends at 1,000, and we want to say dx, the delta x, times f of 1 plus k times dx. Do a control equals. There's the answer of those 1,000 rectangles being added together. Let's take a screenshot, and then let's take a look at the Excel spreadsheet that we had last time and compare. So insert the picture. We'll compare with this number here that we had last time. Hopefully, the numbers match up, at least as far as we have reported here. 0.69289724, and if we ask Excel for more decimals, they would probably match these. So this is a method we want to use now. Instead of having to look through 1,000 cells on a spreadsheet, we can compact the sum so that the calculator can handle the calculation very fast. Here are a couple of properties of sigma that come in handy from time to time as we deal with sigma notation. The first says that if I have the sum of a constant times my expression in terms of k, I'm allowed to bring the constant out in front. Let's take a look at a quick example that verifies that. Let's say I have the sigma of 2 times k, where k starts at 1 and ends at 4. The rule says that's the same as bringing the constant out in front and maintaining the expression in terms of k on the inside, k starting at 1 and ending at 4. Let's verify that those indeed are the same. The first one would be 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. If we expand the second sum, that 2 is out in front, and I would take 1 plus 2 plus 3 plus 4 on the inside. And I think it's very clear if you just expand the right side, you'll get the left side. The second property says that if I have the sigma of a sum, it's the same as the sum of the sigmas, meaning I can more or less distribute the sigma to a sum or difference inside. Let's do an example to make sure that makes sense. We take the sigma, let's do 1 over k plus k is our expression on the inside. And again, we'll have k start at 1 and end at, let's stop at 3 this time. The rule says that would be the same as the sum of k equals 1 to 3, 1 over k, plus a second sigma. Again, k starts at 1, ends at 3. This time k would be on the inside. Let's verify that these are the same. So when k is 1, you would have 1 over 1 plus 1. Then when k is 2, you'd have a half plus 2. And when k is 3, you'd have a third plus 3. If you evaluate these on the right side separately, you'll have 1 over 1 plus 1 over 2 plus 1 over 3. That comes from the first one. And then the second one would be 1 plus 2 plus 3. And if you just rearrange the terms, they would be equivalent. There's one last property maybe that should be mentioned, and that's if you have the sigma of something that starts at 1 and ends at finish, and all that's inside is a constant. Okay, we saw one of these a couple slides ago. Okay, this one right here. We started at 1 and we ended at 4. Then there's a shortcut to evaluating that without having to write it all out and multiply. So all you have to do is take your constant and multiply it by finish. But remember, k has to start at 1 if you're going to use this rule. So let's do a quick one. So let's do sigma of 7, where k starts at 1 and ends at 5. So this should be, by the rule, equal to 7 times 5, or 35. And this is the same as doing what? Adding 7 5 times. So 7 times 5 is 35, and 7 plus 7 plus 7 plus 7 plus 7 is 35.